Okay, so today we're doing a kinematics problem. The basics of the problem is that we have two people jumping on a trampoline. The first guy jumps 1.5 times the height of the second guy, and the second guy leaves at 4 meters per second. And then we're solving these three problems. So like how I like to solve a kinematics problem is simply create this sort of chart here, and this will help get your thoughts in a line and figure out what you're solving for. So in this case, for problem A, we're solving for person two's jump, and we have to choose an initial and final state that we want to use in these equations. Right? It's good to choose states you know something about. So let's call the initial when they leave the trampoline because we know how fast they leave the trampoline at. And since we're trying to find information about how high they jump, let's talk about the apex being the final, right? So these are two important states in the system, right? So the difference between these systems, delta y, is what we're trying to find. Vi, we know is 4 meters per second from the problem statement. At the apex, we know that they have no velocity, and gravity in free fall is negative 9.8 meters per second squared. Now, since we have three values in this chart, that means it's a kinematics problem that allows us to solve for the other two values. So to solve for delta y, the easiest one to use is this one right here, Vf squared equals Vi squared plus 2a delta y, right? Simply plug in 0 here, and you get 4 squared is equal to 2, or sorry, plus 2 times negative 9.8 times delta y. And if you solve for delta y, you get 0.816 meters, right? So that's our solution to problem A. Similarly, let's talk about uh, the second one. In this case, we're talking about person one, right? We know their initial states and final states since we're talking about since we know stuff about how high they jumped, it's probably a good idea to keep the same as before. We know that person one jumped 1.5 times person two, so we simply multiply this by 1.5 and you get 1.224. We don't know Vi, that's what we're trying to find. We know Vf is 0 at the apex, and we know Ay is negative 9.8 meters per second squared. And similarly, we can use this same problem, same equation rather, to solve for Vi, right? Because instead of solving for delta y, we have delta y and need to find Vi. If you follow a similar process, plug in 0 here, etc., you can get 4.898 meters per second. Right, so that's our answer to B. And then finally, we want to figure out how long person one is in the air. Right, so in this case, it's a good idea to change what the initial and final states are. Right, we want something that fully encapsulate how long they're in the air. So let's call it the initial state when they leave the trampoline and the final state when they return to the trampoline, right? So a full jump. Delta y in this case is no longer 1.224 meters because it's the change between when they leave and they return, right? Since they leave and return to the same height, that's 0 meters. We know that the initial velocity is what we just got here, 4.898 meters per second. Vf we do not know. Ay is negative 9.8 meters per second squared. And then finally, we don't know delta t since that's what we're trying to find. However, since we have three values, we should be able to solve for any of the other two. Since we're trying to find delta t, a good one that doesn't include Vf is delta y is equal to Vi delta t plus 1/2 a delta t squared. And then if you plug in your values, you can see you get a quadratic equation. And solving the quadratic equation, you get two solutions. And you can try this for yourself. You'll get delta t is 0. That makes sense. It's simply saying that you leave and return. The time when you have delta y being 0 is the same thing as not leaving the trampoline. That makes sense. The other solution is when you get delta t is equal to 0.99 seconds. And that's our solution here. That's how long it takes for them to actually jump. Right? So we've used these charts to help us solve for all the values in this problem.